Okay, so we've gotten started in section 4.5. We know a few things about imaginary zeros, but what we haven't done is we haven't consolidated the entire deal into the one full-blown process, the same way that we have with finding real zeros. Remember that when we found real zeros, we basically had to set up our series of factors and then do division over and over again in order to be able to find what was left. The process for finding real zeros or imaginary zeros, complex zeros, is very, very similar. So this is the second section of 4.5. I'm going to call it 4.5b. And without further ado, here's the first problem. F of x is equal to x cubed plus 3x squared plus 4x plus 12. Okay, now I'm going to put a little arrow there because I am actually going to come back to this after we solve this and show you a way that we can use some of the things that we already know to make our lives a little bit easier. But first of all, let's do it by the book. We need to be able to factor this out, and what we are given that we have a 0 at x is equal to 2i. Okay, so this is a third order polynomial, so that means we have 3 complex zeros, and we have one of them given to us already. And by the complex conjugate theorem, that one that I referred to as the buy one get one free rule last time, we also know we have a 0 at negative 2i. So we actually have 2 out of 3 so far, and that ain't bad. So let's set it up. F of x is equal to x minus some number a, which is 1, 0, x minus some number b, which is another 0, x minus some number c, which is our last one. We plug in what we already know. We have x minus 2a, or 2i. We have x plus 2i, x minus negative 2i. And finally, our x minus c, which we don't know. All right. Now, instead of dividing x minus 2i and x plus 2i into our original function right here, what I'm going to do is I'm going to first FOIL these guys together so that we have a simplified polynomial with all real terms. And that's going to make our life a lot easier there. So let's multiply these two guys. I'm going to change colors so we know what we're talking about here. We're only talking about these first two terms. FOIL them out. We get x squared plus 2ix minus 2ix minus 4i squared. Okay, plus 2ix minus 2ix, they cancel out, which you would expect because we essentially have a difference of squares here. And minus 4i squared becomes plus 4. So what we have here is our function is actually equal to x squared plus 4 times this x minus c. X squared plus 4 I can definitely divide into my polynomial. So x squared plus 0x plus 4 going into x cubed plus 3x squared plus 4x plus 12. All right, x squared goes into x cubed, x times. Multiply it out, we get x cubed plus 0x squared plus 4x. All right, so now subtract, we get 0, and now we have 3x squared and plus 12 here. You know, formally I should probably have that up here. There, let's make that pretty. Okay, so 3x squared goes into 3x squared plus 3 times. 3 times x squared is 3x squared. 3 times plus 4 is plus 12. Subtract 0, 0. So what we're left with is x plus 3. So we've finished factoring out our polynomial. F of x is equal to x plus 2i, x minus 2i. I believe further up on the page I might have done x minus 2i and x plus 2i, but it doesn't really matter on the order. And then our last remaining factor is going to be x plus 3. So our zeros are going to be at x is equal to 2i, negative 2i, so plus or minus 2i, and negative 3. So now we have that fully factored out. Okay, that one was a little bit simpler because we only had an imaginary part of our complex zero. We did not have a real part of it. We did not have, for example, 2 plus 2i. That's going to be our next example. Now, just to show you how using some of your old skills can come in handy, I'm going to approach this by a different manner real quickly. You may notice that this is a tetranomial that we can actually factor out by parts. You pull out x squared out of the first two terms, you get x plus 3. You pull a 4 out of the last two terms, you get x plus 3. So you can actually factor it out as x squared plus 4 times x plus 3 that way. So does that make it bad to factor it out that way and then get your 2i and negative 2i? So x minus 2i, x plus 2i times x plus 3. Does that make that bad to do it that way? No, absolutely not. There's more than one way to skin a cat. But the way that we did it first is the more formal way that will always work. You're not always going to be able to factor it by grouping, but hey, if you are, make your life a little bit easier and still get the right answer, go for it. So let's try a problem where we make it a little bit more complex. No pun intended. Okay, yeah, I did mean that. F of x is equal to x to the fourth minus 2x squared plus 16x minus 5, or minus 15, sorry. I'm going to go ahead and erase that, minus 15. Okay, now the piece of information that we are given is that x is equal to 1 plus 2i is 0. Okay, now x is equal to 1 plus 2i. That's a little bit more complex than what we were dealing with before. Before we only had one term, now we have the 1 plus 2i. So it makes the math a little bit longer, but it doesn't make the process really any different. Okay, what this tells us by the complex conjugate theorem is that 1 minus 2i is also a 0. Okay, so we have bought one and gotten one free. Secondly, since this is a fourth order, we expect 4 linear factors. So let's see what we got. Set it up the same way. F of x, x minus the first 0, x minus the second 0, x minus the third 0, x minus the fourth 0. All right. Now we know 2 of our zeros, and when we plug these in, it's not very pretty, but mathematically we're still doing the exact same thing. X minus our first 0, which is 1 plus 2i. Times x minus our second 0, which is 1 minus 2i. Then finally, our x minus c, x minus d. Okay, so what we did in our earlier problem is that we multiplied those first two terms so that we didn't have those imaginary parts, so that we had all real numbers. And we are going to do the exact same thing again. Okay, we're going to do the same process. All we got to do is FOIL these out. It's going to get ugly for a second, and then it's going to, things are going to start canceling out and simplifying. Okay, first terms, x squared. Then minus 1 minus 2i times x minus 1 plus 2i times x plus our 1 minus 2i times 1 plus 2i. Okay, what I'm doing is I'm neglecting that x minus c and x minus d for the time being. I'm really only worried about multiplying those first two terms. Okay, let's simplify this out. X squared minus x plus 2ix, so we distribute that x, minus x minus 2ix, so we distribute that x, and then plus, and we have to FOIL these last two binomials again. So the first two terms, 1 squared plus 2i minus 2i, and then minus 4i squared. Okay, so let's see what we can do, because we can start canceling a lot of these out. Plus 2ix minus 2ix, plus 2i minus 2i, and then minus 4i squared becomes plus 4. So what this becomes is x squared. We have minus x, so we have minus 2x, and then plus 1 plus 4, so we have plus 5. So our polynomial is that times x minus c, x minus d. Okay? The exact same process that we just did. It just looks a little uglier. We're going to do the exact same thing again. We're going to divide x squared minus 2x plus 5 into our original polynomial. So, without further ado, let's go ahead and do that. X squared minus 2x plus 5 going into x to the fourth, and we don't have a cube term, so I need a placeholder, plus 0x cubed minus 2x squared plus 16x minus 15. Okay, we divide this out. X squared, x to the fourth, minus 2x cubed plus 5x squared. 0, 2x cubed, minus 7x squared, carry down to 16x. That means we get a 2x up here. X squared goes into 2x cubed that many times. Multiply it out, we get 2x cubed minus 4x squared plus 10x. 0, negative 3x squared plus 6x minus 15. Give myself a little bit more room. And then finally, our last step, x squared goes into negative 3x squared, negative 3 times. Multiply out, we get negative 3x squared plus 6x minus 15. That doesn't look like a 5 at all. There we go. Close enough. 0, 0, 0. So what we are left with as our x minus c times x minus d is this guy. So we are left with that, which isn't really factored, but we can factor it relatively easily. That is x minus 3, x plus 3 times x minus 1. So extend our page out a little bit. And just to sum up what we've got is we have these two linear factors, which we started out with right here. So x minus both of our complex zeros. Our function factored out is x minus 1 plus 2i, x minus 1 minus 2i, and then finally our x squared plus 2x minus 3. And then as our final step, our little coup de grace, is to factor this guy right here. So x minus 1 plus 2i, x minus 1 minus 2i, then finally x minus 1 times x plus 3. And there we go. For practice, what I'd like you to do is on page 388, number 1, number 9, and number 17. Okay? Now, just as a side note, we already know that if we multiply these two guys, what we're going to get is x squared minus 2x plus 5, and then we can leave these guys factored since they are not complex zeros, x minus 1, x plus 3. So we can write it out like this if we are limited to not having imaginary numbers, and the technical term for this is keeping it real. On that, I'm going to sign off.